Thanks for BlueHat for bringing me here to Tel Aviv. It's a beautiful venue and a really bang-up job you guys did on all the decorations out there. My computer went to sleep, so just go ahead and wake it up. Are we good? There we go. So the topic of the talk is going to be about supply chain security with the subtext of if I were a nation state. And so some people have asked me, is this in response to the big Bloomberg article that came out? Actually, the topic was picked about a month before that article came out. I was invited to give the talk, and I said, hey guys, what do you want me to talk about out here? And they're like, oh, it'd be cool if you gave a talk about supply chain security. I was like, sure. And then like about a month later, that article comes out. I'm like, okay, well, that's pretty topical. We're going to have to make a couple adjustments to the talk. But overall, the idea is essentially if you had a large amount of resources, more than I have, what are the sorts of things that we should actually be worrying about in terms of supply chain security? So first, a little about my background. I'm a hardware guy. That means that when everyone was doing the dot-com thing, I was wasting a lot of time building stuff like this, all the wires, all the sorts of things. Time passes. A lot of my friends go off and do more software stuff. People put away their soldering irons. People start outsourcing their supply chains. And eventually this comes to the point where people start putting, using hardware as security roots and as enclaves. And so if I'm to be believed, that phrase there roughly translates to, in the land of the blind, the one-eyed man is a king. So in the world where everyone had forgotten how to solder and how to build circuit boards, this is actually a picture of a board I put inside the original Microsoft Xbox to extract the security keys that were being passed on a high-speed bus between the South Bridge and the CPU. And back then, it was relatively easy to go ahead and build one of these things. It took just a couple weeks, and you can pull out the keys now. You have to do much more heroics to go ahead and pull keys out of the trusted roots. After that, sort of little stint, playing around with the Xbox, I decided I wanted to do something a little different, so I spent a few years designing silicon. This is a nanophotonic integrated chip that I worked on at a company called Luxtera, and the really interesting part about this is that I got exposed to the roots and the nitty-gritty of how to actually design transistors on silicon, how to do layer stacks, how to manage fab, how to build packages, these sorts of things, and that will become relevant. That experience will actually comes into relevance later in the talk. Nowadays, I mostly spend my time building systems, so here's a few of the things I've sort of played around with in recent years, which means basically I spend a lot of time dealing with supply chains. And supply chains are inherently not a friendly territory. So this is an example of a chip that was actually sent to me by a friend. This is a ST, it purports to be a sort of a secure microcontroller. He bought a bunch of them. They weren't behaving. He sent them to me. Took the top off the chip, put it in a microscope, and found out that on the inside, it was not actually that microcontroller is labeled on the inside. It was actually an LCX244, which is like an 8-bit TTL buffer. Not a very interesting chip, but it tells you about sort of already there's a bit of subtext about people playing shenanigans in the supply chain. Another problem I had was I had to source SD cards, buy them. I had some SD cards from a vendor called Kingston. They weren't behaving correctly. They weren't according to spec. And so I went to the gray markets, bought a whole bunch of them, digested off the top with acid, took pictures of all the chips on the inside, learned more about the structure of the cards, and found some really interesting sort of correlations between what was purporting to be a real chip and what were some patent fakes, for example. So there's a lot. The level of sophistication people are going to build these sort of fake memory cards is quite high. They're stacking chip on chip, doing wire bonding, encapsulation, packaging, and marking. Another example of a problem that I had was I built a little board, it's open source, that has an FPGA on it, and I had a problem where in production about 3% of the boards were failing a particular part of the test. We put them aside. Later on, they were sent to me, and one thing I finally noticed about them is that all of the FPGAs that were failing had this little square here. If you look over here, here's a bigger picture of this square. This square here is someone had put it in a laser etcher and just blasted off what was underneath here, the letters ES for engineering sample. So someone had gone and recovered engineering sample FPGAs, or they're meant to be ground up, had blasted off the letters and put them back into the supply chain. Of course, we had to check the part number before it goes in, but the worker just saw square. It's not, it didn't say don't not accept the square, so the part number was valid. It got put onto the boards. So I brought up the issue to the contract manufacturer I was working with at the time, AQS. CEO was sitting there, and then like all the managers and that sort of stuff. And it was really interesting. His first reaction was he looked around the table and says, okay, if anyone in this room is responsible for this, you have one chance now to fess up to it. The punishment will be less severe, right? So the first thing he knew was that inside his own company there could be people playing the cheating game, and he wanted to clear himself of that first, right? So of course, no one fessed up to it, and then we started looking down the supply chain. Who are the distributors? Going all the way back to Xilinx. Where are the places the injection could have happened? And people, like when we called up the distributors, they're like, oh, it must have been the courier. The courier intercepted the packages and took the chips out and swapped them. Oh, it must have been in your warehouse. Someone broke into your warehouse and stole the chips. The line workers swapped it out at the line or something like this. So just the blame game was going back and forth, back and forth. It turned out at the end of the day, we had a couple of distributors for the FPGA. One of them was this Chinese company. And most likely it came from that one and not Avnet. We tried to report the issue to Xilinx. Unfortunately, this Chinese distributor had so much leverage on that supply chain, Xilinx couldn't afford to disqualify them. So they continued to sell through those guys, and we ended up at a settlement where they just sent us replacements for the chips that were bad. So why would they do it for just 3% of the chips? Why would they blend them in? It seems like a lot of effort and a lot of risk for what seems like not a lot of reward, except if you consider the fact that the distributor margin's only about 3 or 5% to start with. If you blend them in at a rate of about 3 to 5%, you've doubled their margin, right? So it's actually a huge amount of money for those people who are involved in the supply chain to pull off an attack like this. And also, when you blend it at a rate of a few percent, it sort of kind of mixes in with the other noise of manufacturing. Like I said, when the issue happened on the line, we just set them aside. It didn't set off any red flags. Like 3% could be a soldering error, could be something else. So it took us a long time to even catch the problem. So that's sort of a little bit of background about how supply chains can be hostile even if security is not involved. Now if we want to think about sort of a security basis for supply chain attacks, let's talk a little about sort of like the whys, the whats, and the wheres of supply chain attacks. Like why would you want to do it? What might you do? And where might it happen? And this is going to be the bulk of the talk. So why do you want to attack a supply chain? Well, there's obviously people want help getting in. So you want to have backdoors inside hardware to assist with getting your rootkits and exploits in. Sometimes you want to get things out. It may be difficult to exfiltrate data, or you want a more subtle way to exfiltrate your data. Or you just want to sabotage equipment through some sort of selective defeat or destruction of equipment in the case of cyber warfare or ransomware or something like this. There's probably other reasons as well, but we'll just pick these three as a sort of a basis to talk about supply chains. So getting in, a backdoor can serve as a beachhead for a rootkit, remote system access, or persistence. As the previous talk has demonstrated, some vendors already build backdoors into the systems and sell them to you. So the work is already done. But in some cases, people want to go ahead and, for example, tamper with the management engine, add some implants inside of the management interfaces to go ahead and assist with getting backdoors into the hardware. Exfiltration is also another reason. So this is people I'm pretty sure are familiar with the ANT catalog from the NSA, from the Snowden leaks. This is an example of an implant you can put inside a video cable that will go ahead and radiate what's going on the screen, and so that an attacker nearby can go ahead and exfiltrate what's the content of the screen with the radio receiver. There's also other ways. For example, if your hard drive reports X amount of gigabytes and you do a secure wipe, but actually there's a little cache of data on the side that's unwipeable, it can be used for exfiltration of data as well. Mobile has a unique opportunity for exfiltration of data. In particular, mobile devices are very helpful for leaking the information on targets. And there's also enhanced opportunities in the mobile scenario for direct access to the hardware, so evil maid style attacks, and near-field access to the hardware. And in terms of sabotage, of course, you can imagine scenarios where if you could have a selective defeat of hardware based on remote command, that could be extremely useful, particularly to nation states interested in engaging in cyber warfare or ransomware. So now let's talk a bit about the what. This is a bit of a big diagram. We're going to go through each of these blobs one at a time. The idea is, what might you do to attack a supply chain? And this diagram, it has two axes. The vertical axis is, hold this here, is the detection difficulty, right? So I sort of have it I ranked it from easy to hard. So easiest is visual. You just look at it and you're like, huh, there's something there that shouldn't be there. Harder is sort of you need some equipment, specialized equipment to either an X-ray or you have to use a meter to detect the presence. And on the bottom, the most difficulty would be if you had to pull off the chip, put in a scanning electron microscope, and look for the implants. On the other sort of axis is sort of the execution difficulty. So, on the right-hand side, the easiest sort of attacks take seconds to execute and cost less than $1. And the hardest ones can cost millions of dollars and take months to plan and perhaps pull off. And these sort of dashed lines here, I want to sort of, if you were to spin custom ICs to make these attacks a little more effective, it gets a little more expensive, but on a log scale, it's sort of just pushes out a little bit further into that region. So let's start with the first sort of easiest stuff, component substitutions, right? These are just taking components out and swapping them for other components. Super easy to execute. You would think that they're relatively easy to detect, so they ought to be on the easy side, but something can be very hard to detect. So if you ever looked at a circuit board, you'll see plenty of resistors and capacitors. These resistors have no labels. They all look the same. They could be 0 ohms. They could be hundreds of mega ohms. You have no idea. Capacitors look all the same, basically. There's no way for you to really tell what they are unless you pull them off. In fact, if you just put a meter on the board and try to measure it, other circuits around these can mask the actual value of those parts as well. So it can be difficult to tell if a component has been swapped. And this is actually, in manufacturing, this is a classic problem in itself. I always sweat bullets that not someone's attacking my supply chain, someone just put the wrong reel in the machine. Now I've got the wrong resistor in the wrong spot. So the mechanisms that can be in play when you do a bomb swap is that you can modify, for example, bootstrap options. Chips will determine perhaps which interface to read the code from initially based upon a strapping resistor. Changing that resistor from 0 ohms to a very large value or vice versa can change the boot behavior. It can also help with things like if you want to do remote side channel attacks. If you reduce the amount of capacitance on a particular device, it makes the supply noise much larger, and you can go ahead and assist with those styles of attacks. For also row hammering, a lot of people here, I think, are familiar with row hammering. It's very dependent upon the structure of the DRAM chip itself. This is a micrograph of the DRAM chip, and essentially you're swinging the adjacent wires around to try and induce a fault inside a memory cell. So the solution to hardening against row hammering part of it is, well, why don't we just make sure we accept only authentic chips that are proven to be hardened against row hammering. So this is a wonderful memory. It's by Kingston. It's got the authenticity label. It's got the labeling, all that sort of stuff. Except, you have to look a little bit deeper than that. Fun fact, Kingston doesn't have a fab. They don't make memory chips, so how is it they have chips with their name on it? If you go to a site like DRAM Exchange, they actually post the spot price of DRAM. You can check it on it. It's like a stock market kind of thing. And you'll notice that one of the memory chips is much, much cheaper than the others, and it has this term ETT after it. What does ETT stand for? Well, ETT is actually for RAM that's effectively untested or effectively tested or untested. It turns out that RAM manufacturers can oftentimes produce memory at a rate faster than they can test them. So they come off the wafer fab, and there's a backup at the testing machines. So for them to go ahead and try to monetize their fabs faster, they'll go ahead and sell chips that are not tested or effectively tested, so they're just spot tested. They're blank and unmarked, and then other manufacturers pick them up and are supposed to, Scouts Honor, test them, mark them as their own brand, and then sell them out. Guess what? This is a perfect opportunity for people to go ahead and swap around chips inside the supply chain, even though they may be marked as one thing. They could have another chip on the inside. Another sort of attack that can happen through a simple bomb swap is a mobile device identification. So if you were to take a radio signal from a mobile phone, put it in a spectrum analyzer, and look at it, you'll see a particular shape to the spectrum coming out. This shape is actually almost required by law. You can't transmit in the sidebands, And this, this actual shape on the top is very consistent from device to device. And part of what allows you to achieve this is there's actually a passive filter on the back end of your power amplifier of your mobile phone to create that shape. If you were to go ahead and tamper with that filter, you'll actually see sidebands start appearing on the edge in this band here where it shouldn't be. And sort of like in that Matrix where they have that red woman who walks through the sea of black suits, since everyone's phones here passes verification, the one person who has a tampered radio that doesn't have the filters on it is going to stick out. You'll know that that person is near. You can sort of identify a particular target through a modified RF filter. So that's component substitution. Let's talk about adding components. So let's just put another component inside the device that shouldn't be there. And this is the one that a lot of people think about. This took the headlines with the Bloomberg Businessweek. Just put this little component on the inside. If we make it really small, maybe no one will notice. Or NSA had created implants that go inside of the Ethernet jack or inside USB jacks to go ahead and exfiltrate data or do something else to the machine. And so adding components is relatively easy to detect. You can either see it in there or you can see it in an X-ray. So let's talk about X-rays a little bit. So this is a Novena motherboard, a circuit board that I made once upon a time. I had a friend with a CT X-ray machine. We stuck it in there, decided to look around, poke around, see what it looks like. This is what the motherboard looks like on an X-ray. So there's some things that are really obvious. You look inside, like the Ethernet ports, and you see the transformer. This is perfectly normal. These are the transformers on the inside. They're the hybrid that are required by spec. But then if you look at, for example, these are the chips, right? You say, okay, well, what I'm looking at here, like, what's going on? Is this thing here the silicon? Actually, it turns out this is not the silicon. This is actually a large solder pad underneath the chip, and the solder itself is very dense. It blocks the X-ray, so it actually masks the presence of the silicon. It's very hard to tell where the chip is inside an X-ray. Which brings me to the next interesting sort of exploit space, which is adding a chip inside of a package, right? So multiple chips inside packages is a sort of well-established technology. As I had sort of alluded to in the micro SD card example, there's chips on top of memory chips to control them. In fact, today you can get sort of 16, 17 chips inside a single package when you have your little high-density micro SD cards. It's a very mature technology. And so the thing that they use to do this is a technology called wire bonding. If you were to take a standard, for example, dip chip, take off the top, you would see the silicon on the inside, and you would see these little wires coming off the edge of the chip. Those are the wire bonds. If you were to look inside of a USB key, for example, they're made by taking chips, sticking them directly onto a circuit board, and wire bonding them down to the circuit board and encapsulating them with plastic. This is what the wire bonds look like in sort of a microscope view. This is the chip, and you can see these little thin wire bonds coming off the chip down onto the circuit board. Once the wire bond is done, the chip is usually encapsulated. So in the case of chip on board, you get the little black blob on it. In the case of actual chips, it goes into overmolding machines, so it looks a little bit nicer. Wire bonding process itself, let's see if we can get this video to start, is actually very fast. So this is actually a wire bonding machine. It's not in a clean room. It's me with the camera standing next to them in regular street clothes. Happens very quickly. The operator just swaps in boards. It finds the chips, goes ahead and puts the wire bonds down. This machine here, you can buy it on the second-hand market for tens of thousands of dollars. It's not super expensive. If you want to do a custom wire bond, this guy here programs the machine. He does it. He basically has like an image. He sees through the microscope. He designates where the wire bond goes, and he hits a button and it remembers those positions. And you can see here the actual specification is a PNG that I emailed to the guy. And he's looking at it on his phone, counting where the wire bond should go. He's going to go back to the screen and sort of identify where those bonds go. And then once he designates all the points, the machine remembers where all those wire bonds should go, has a little bit of vision recognition to make sure it's aligned up, and it just replays and replays and replays and replays to go ahead and do it. So wire bonding is very accessible. It's very versatile. You can do chip on chip. And so now when you want to go ahead and look inside of chips and sort of look for implants, there's a bit of a challenge because actually some chips intentionally have multiple chips on the inside. This is an example of a mobile phone chipset from MediaTek. I put in an X-ray just so I was curious to see. I actually just want to know how big the die was. And I was surprised to see, if you know how to read these things, you'll see there's about 6 or 7 separate silicon pieces inside of here. Each of them are from different manufacturers. And I was like, okay, why do they do this? If you look at their SKU matrix, it turns out they offer the same part as a single package with multiple memory options, different power amplifier options, different radio bands. And so instead of spinning a bunch of different masks for different SKUs, they just put them on a single substrate, wire bond them together, and then sell them to you on the outside as a single chip. So if I were to try and take this and I say, okay, I'm going to put this in the X-ray and try and figure out if someone's got an implant on the inside, it could just be the manufacturing changing vendors for the memory chip, for example. Nothing malicious at all. And then if you want to go ahead and zoom in and say, okay, what's the best I can do to look at the silicon? So I'm playing with the contrast to try to image the silicon. You can see kind of the outline of the silicon here, but the first thing you'll notice is any copper, any sort of metal underneath it immediately masks it out. So the moment this chip is not mounted on a circuit board, the moment the thing goes on a circuit board, you're going to have more and more layers of copper and solder masking out the presence of the chip. So let's take a little closer look at what a wire bond looks like. This is in the 3D view, is a little rendering that I made. It's a chip. The wire comes down, it's put on the chip, it's pulled off to the side, and then bonded on the circuit board. And they just do this over and over again. And if you were to go in an X-ray, you would see sort of like this outline, and then the wires coming off of the chip. Now let's imagine that we want to go ahead and put an implant inside of a chip. On the unmodified version, the wire bonds come straight from the original bond pads down to the PCB. For the implant version, I've gone ahead and just placed a die on top of the die. I wire bond from the pads to the existing pads, and then stitch it back down to the circuit board. Double bonding onto pads is a well-established technology. They do it all the time. If you want to sort of get a man-in-the-middle effect, you can wire bond from the target pad and then wire bond back over it onto the board. That's also a technique that is perfectly fine in wire bonding. If you were to imagine what it looks like in an X-ray view, you would have a second chip on the inside, which, remember, is very hard to see. And the only delta you'll see is that some wire bonds are just a little bit longer inside the X-ray view. So it's detectable but difficult. This is what an actual piggyback looks like in the X-ray. If this is the cross-section of the chip. 8 layers or so, and you can see the stitching of the wire bond going down to the circuit board. If you were able to actually get the edge of the chip and look at an X-ray edge on, you can see the stitching. The thing is, normally it's mounted on the circuit board, so other components would be in the way. You wouldn't be able to get the X-rays through to it, so you have to pull the chip off to get this view. From the top view, all you see are straight wires. There's nothing in the top view that really gives away the fact that this has so many chips inside the stack in an X-ray view. So, wire bond implants leverage mature commodity technology, costs a few $1,000s and maybe a couple weeks to develop, and you can do this with all sort of, either outsourced equipment, or if you're paranoid, you don't want someone to know about your operations, you can insource it for a couple $100,000 and buy the molding line outright. And you don't have to develop custom chips for these exploits. You can use commodity MCUs or FPGAs that you buy in bare die form, put them inside of a chip, and go ahead and have your implant deployed. The problem is it is detectable in X-rays. So there's another technology that's come out called a through-silicon via. So as the name implies, this is a piece of silicon, and there's now a via that goes from the front coming out the back side of the silicon. This height here is about 0.1 to 0.2 millimeters. This is a cross-section of a through-silicon via. If this, maybe about 5 or 6 years ago, this was exotic. Today, if you buy any graphics card that advertises HBM, the high bandwidth memory, they're using through-silicon vias. It's a mass production process. You can just sort of order it from the fabs. So now, if you're to have a through-silicon via chip and you were to execute the same implant, you just bond it on top of the existing pads and you wire bond on top of those, right? There's no extension of the wire bonds. So if you were to go ahead and take a cross-section of this implant, this is the implant IC, and this is the wire bonds, and I'm just going to cut right through those wire bonds here. This is what it'll look like. You have your package substrate, your target silicon chip. This is your man-in-the-middle IC, through silicon vias with bumps going down the chip, and then your wire bonds coming off the top. If you were to look at this in the X-ray view, the unmodified version versus the modified version, you wouldn't see any difference in terms of bond wire lengths. You just have to sort of rely on the hope that you can see this ghostly bit of silicon. Remember, the silicon itself is rather transparent to X-rays. So Wire bond with through silicon via implants does require a bespoke man-in-the-middle chip because it has to match the bond pattern, and through silicon via is sort of a newish technology, so you can't just buy commodity parts. So it's a bit more expensive and difficult to pull off, but it's harder to detect with X-rays. So what about this other packaging technology called wafer level chip scale packages, WLCSPs? This is just a random one I had on my desk. Took a picture of it. You can see it's a silicon die and then literal solder bumps put on the silicon die. This is actually becoming a super popular packaging format. If you look inside of an iPhone motherboard, like 80% of the chips by count use this packaging technology. The cool thing about this is that essentially they've done a lot of the hard work for you in terms of getting an implant in there. You've got the bare die, so you don't have to source the bare die. You've got the things already balled out into large pads. And so if you were to look at the cross-section of a normal device, you can see you've got your solder balls, your target silicon, and then some backside passivation to protect the IC. You go ahead and you throw in your implant. You just go ahead and you just stack it right on top of the bumps, and then you have the solder balls on top of your implant, and now you have basically an undetectable implant on the inside of your chip using through silicon via technology. So if you want to try and detect this through an X-ray, it's going to be difficult to detect because the solder balls, as mentioned before, will mask a bit of what's going behind it inside the X-ray machine. So even if you can tilt the chip a bit, it's a little bit difficult to tell that you have another chip on top of a chip. And if you're to optically inspect, actually a lot of these chips already have a seam on the edge because, as I mentioned before, there's a backside passivation coating. So it's easy to confuse that seam with, for example, what might be another layer of silicon that's been put in between your chip and the chip that's the man-in-the-middle chip between the chip that you want to have on your board. So wafer-level chip-scale implants, the pros of them is they're logistically much easier, actually, than wire-bond implants because for a wire-bond implant, you have to source the target chips in bare chip form. That can be a little bit of a trick. You have to bribe someone. You have to work with someone inside the company to get the bare die out. There's no package to reverse engineer. You don't have to redo a package. It's just the chip. The through silicon vias and the wafer-level chip-scale packages are both commodity technologies. There's no new tech I'm proposing here. This is off-the-shelf stuff. The con is that it requires you to fabricate a custom template for every single chip you're trying to exploit. So you have to make a piece of silicon that has the through silicon vias at the right locations for every single chip you want to attack. I estimate it would probably cost in the mid-hundreds of thousands of dollars to set one of these up. You don't have to do it in a cutting-edge fab. You can do it in sort of a 130 nanometer, 180 nanometer fab to go ahead and build those chips. So it's not as expensive to fab the chip. But the real pro of this is extremely hard to detect. There's almost no X-ray footprint, almost no visual footprint. So that's adding an IC in a package. Let's talk about substituting, very briefly, substituting ICs in a package. This is where instead of putting another chip on top of a chip or using the existing chip, you just get rid of the chip, put your own chip in. So system controllers are oftentimes little embedded ICs. You can go ahead and just swap it out with another one. Another objective you could have is, for example, on every DRAM DIMM, you have a little sort of SPD, a little I2C EEPROM that tells you sort of what the characteristics of that DIMM is. It's supposed to be a certain amount of bytes large. If you put another chip inside that I2C package that has a much larger capacity, as long as you don't try to read or write past the end, the system will never know. You won't detect that issue. And so, and this is a relatively trivial thing to do, to go ahead and take an existing SPD memory, mark it as sort of a lower capacity than it is, put it inside your DIMM, and now you have a convenient little cache where you can go ahead and store keys you want to exfiltrate or code you want to use later on, something like that. So this is also another sort of attack venue that is feasible and useful in certain situations, and very hard to detect because when you look at it in the X-ray, there's one chip, it looks legit, it's inside of a package. And finally, there's the subject of modifying the chips themselves, right? So I kind of consider this the ultimate attack, backdoors inside the IC. Of course, as the previous talk had indicated, some manufacturers backdoor their ICs for you by putting management engines in with all kinds of fun flaws in it. But if someone is trying to harden their chips against you, if you can get backdoor inside the IC, they're very hard to detect, they can be difficult to attribute, and they're of course very persistent. So how would this happen? There's actually multiple insertion opportunities during the process flow of making a chip. So when you start with your high-level chip design at the very top here, you start with a piece of RTL, piece of code, and then either you're the type of shop that owns the set of the tools internally to build that into a mask set, or you don't. And if you don't own those, then you're actually just sending off a netlist to a third-party service, and that third-party service can tamper with the netlist. So it's a relatively easy way to get a backdoor into the chip. Even if you do own the back-end flow, there's opportunities such as tampering with the hard IP and also mask tampering to go ahead and get implants in. So we'll talk a little bit more about each of these. So netlist tampering. So there's kind of two, if you're to split the flows into two major categories. If you're to spin your own chip, there's one called the ASIC, Application-Specific Integrated Circuit Path, here on the left. And the right-hand side is called COT, Customer-Owned Tooling. The big difference between the two is on this one, you've got several extra headcount and spent several $1 million extra to buy those tools that you need to go ahead and turn RTL into a mask set. And typically, it's used only for like high-performance applications where you can justify the investment of COT. For sort of like cheaper support chips, things like server BMCs, disk controllers, set-top boxes, the controllers inside of your memory chips, whatever it is, these Jelly Bean ICs, it doesn't pay off to buy the whole flow. So a lot of times people just hand off RTL to a third-party service to go ahead and implement those chips. Here's an example of one vendor that advertised a service called SockIO Next. They did about a 1.3 billion revenue in 2016 estimated, and they, from their own page, they have like, here are the stages where you can hand off a design to us. You could just hand a specification, we'll do the whole thing for you. You can hand off RTL, or you can just hand off a netlist. Of course, on this whole back-end side here, from physical design all the way to testing to the shipment, there's opportunities to put stuff inside. In fact, what you often find is that these ASIC vendors will put backdoors in for you, not under any malicious guise, but just to help them with testing. It's their responsibility to yield to you a working chip, and so they're going to go ahead and put sort of effectively test access ports on the inside, which are not going to be within the RTL that you've hardened, and can go ahead and serve as a backdoor. So okay, if you care about security, you're going to do COT, right? So I'm safe with COT. The problem is that even if you have all the tooling yourself, you have these blocks that are called hard IP blocks. This is a view of what you might look at, on the back end of your place and route. You have these small little boxes here, which is all your standard cells that are being placed down, your NANDs, your flip-flops, whatever it is. And then literally you just have this block called this blob of SRAM, right? And the foundry will not share with you the actual layout of the SRAM. They insert it to you after you hand back to them your mask pattern. So when you ship a mask pattern to the foundry, it's got these big holes in it for things like RF and analog, PLLs, ADCs, DACs, and band gaps, things like RAM, things like ROM, things like eFuse. So the reason why the manufacturer doesn't share these with you is that RAM density is one of the metrics that really drive the cost of a chip. Chips have a lot of RAM on the inside. They spend a lot of money and effort optimizing those layouts. They're not going to let that layout leak to another foundry so you can get that edge in terms of cost. So they're just not going to share with you what those blocks look like. You just have to trust them that those blocks perform to spec. eFuse is another thing that's very hard to get from the manufacturer review. I have accounts from people who work for very large companies that are very security conscious, and they want to get the eFuse blocks to audit, and the best they can do is they can get test chips back and they have to send them to a third-party service to delayer and reverse engineer to make sure that they're working correctly. The manufacturer will just not share with you the eFuse IP. Pad rings also as well, for various reasons, manufacturers don't want to share those with you. So basically, even if you do a COT tooling flow, everything you need to backdoor your RTL is going to be a hard IP block, and you're just trusting a manufacturer, a fab, not to do anything wrong with it. Even if you were able to convince a fab to give you all of those blocks and you can review the GDS2 mask before it goes out, the masks themselves go through a lot of processing. So if you were to draw well, let's think about the problem in the first place. If people heard like, okay, we're at 14 nanometers, something like this, and that's a number people bat around. How big are the photons they use to image that? 193 nanometers. Okay, you're using photons that are this big to make transistors that are this big. Something doesn't work out there, right? Some magic has to happen. So when you have your mask pattern that looks like an L like this, it gets turned into this green outline, which then turns into this red printed outline. This is not even at 14 nanometer. To do the 14 nanometer stuff, they actually take your mask and fracture it into multiple sub-masks and use a whole bunch of other techniques to do this. And this is all done after you hand your mask to them. The fab runs a whole bunch of algorithms to just tamper with your data, essentially, and turn it into something they can manufacture. And then also, the masks themselves have to be perfect, right? Masks aren't born perfect, so there's a whole industry around editing masks after they're made. So this is a manufacturer, they're advertising how they can go ahead and take masks that have broken lines and fill in the lines that are broken, they have excess material, and remove the excess material, and they can go and print it. Well, guess what? Mask editing is the perfect opportunity to go ahead, and if you can control that mask editing process, even if you've vetted everything all the way down and you don't control that mask editor, someone can go ahead and tamper with your layout. What can they do? For example, dopant tampering. There's a paper you can check out where essentially you can, instead of, and this one's a very difficult one to detect because there's no morphological change to the polysilicon, no change to the metal layers. All that's happened is the trace amounts of atoms that control whether you have an N or P-type transistor have been modified, right? So this is a very difficult one to detect, and this one can be done entirely at a mask level edit. Spare cell rewiring, so ASICs are expensive. You don't tape them out without any sort of silver bullets in your pocket to save you in case of a bug. So when you have your final layout, this is an example of all the little standard cells. They'll look for empty slots. The tool will automatically insert spares, things that aren't connected to anything else but already have essentially all the logic wired in. So later on, if you feel like, oops, I screwed up my logic, you don't have to spin a whole set of masks. You just have to make a couple mask layer changes to go ahead and fix your design. And so this is oftentimes done as a mask edit. Guess what? The thing that's good for the designer is also good for the attacker. And you can do just simple, subtle things like signal bypasses. If you look at the design of a flip-flop standard cell, it turns out every standard cell gives you both the true and the inverse of the signal. This is just a feature that every cell has built into it, whether you want it or not. So if you want to take a signal and invert it, you don't have to add anything. You're just changing the contact point from the true output to the not true output, right? So that's a pretty useful primitive to have. Or if you have a multiplexer and you want to just go ahead and say, instead of, if the hash checks out, go from signal A, or if not, go through signal B. You want to always go through signal B. It's just a matter of changing a contact from being here, the select pin, just wiring it to power or ground. They're both next to each other. There's just a tiny little change in the mask. And remember, these masks have billions and billions of features. You're looking for a literal needle in a haystack. So that's sort of the what you might find people doing to attack on a supply chain. So the question now is where can these sorts of things happen? So let's first start with you, right? You're wherever you are, and you want to order something that comes from a distributor via a courier. There are documented attacks where people intercept packages en route via FedEx, open them up, put an implant on the inside, and then ship them on to you. So that's a well-known issue. There's also the issue that, particularly if you're ordering from Amazon, you have returns that go back to the depot. So you can have a hacker inside the customer base buying stuff, and if they don't want to be very specific about it, or they just want to be specific within the distribution region, they can go ahead and tamper with the product, say it's broke, send it back, and Amazon will happily sell it to someone else without checking it again. And so even if you have tamper stickers, for example, they can be removed. This is actually a really great talk by Dimitri Netos and a bunch of other guys at 35C3. I encourage people to check it out if you want to learn more about sort of the attacks they can do at this level, called wallet.fail. And they demonstrated they can remove the tamper evidence seal and sort of the chaos that these tamper evidence seals and the attempt to try and secure this can happen in the supply chain. So that's sort of at the distributor and courier level. So now let's think a little bit deeper into the supply chain. How big does that attack surface go? Well, where does the distributor get this stuff from? It comes from a manufacturer. It goes overseas. It goes through customs. There's certain single points of entry, right? And so this is where we sort of now enter these sensational stories about the big hack, right, from Bloomberg Business Week, because it's actually just a huge attack surface, places where people can go ahead and inject implants. So not only do you have customs and the factory that does the box build, the box build factory has to buy their components from other factories. There's distributors, they're interacting with the gray market, and then you have the test and IC packaging houses, which are separate from the chip fab houses, which are separate from the mass prep houses, which are separate from the actual house that does your design. So all of these different actors are opportunities for someone to go ahead and put an implant. So the question now becomes, how well can we target that implant? How far away can we get from a particular target and say, I just want it on that one. Not everybody, but just that guy, right? And so there's a trend in supply chain logistics called build-to-order, or mass customization, or custom turnkey order, just some of the terms for it. So if you order something on the Apple Web Store, they'll send you a tracking number, and it comes from Shenzhen, China, and you can track it all the way to your doorstep, right? The world is great, because now the world is very small. The world is also very targeted. So essentially, I've visited some of these flavoring facilities inside China. There's a facility called CTS that I went to once. And for example, when you order a laptop, you say, I want to have the secure hard drive and the hardened OS. I want to have the secure enclave and all these other features. Guess where that gets built? There's some guy inside this factory who's just going ahead and putting all these things into the laptop for you next to all the other ones. And I can walk into those factories and just sort of take a look around, right? So another thing is, for example, during the fulfillment process, they use a system called pick-to-lights. So the blue bins in the back are the inventory, and then the packages in front are the boxes going to customers. What happens is the worker just gets a printed order. There's a bunch of words on it, but basically barcodes. They scan the barcode, a light turns on, they pick it out of the bin, they put it in the box, they seal it, they ship it, right? So the neat thing about this from a supply chain attack standpoint is that you don't need to buy off any of these workers to go ahead and get them to put something into a very targeted box for a particular customer. You just need to be able to go ahead and install another bin at the end, install another code for the software that has your special inventory in it. Those workers continue with their daily operations, and then when a particular zip code comes up, particular customer name, whatever it is, they get the special version versus the regular version. And so it's not like you have to go in the facility and bribe every single person from top to bottom to get this to happen. Just a couple weak points need to be knocked over to go ahead and get a very targeted implant towards a customer. And the other thing I want to note is that swapping chips is actually easy. I mean, if you haven't done it before, it feels hard, but there's people whose day job essentially is swapping chips off and putting them on. There's an example here, a YouTube video you can go and see. Someone basically pulls off the NAND flash from an iPhone motherboard and replaces it within 30 minutes, right? With what looks like pretty simple equipment, and the equipment's not that expensive to do. So from the perspective of do we have to worry about inventory sitting on a shelf post-manufacturing that has a chip swapped on it? Yes, that's a real possibility. That's not something that's hard to do. So people have oftentimes asked me, it's like, hey, what do you think? Is this thing real or not? I mean, so the problem is that everything that leaked seems feasible, technically, right? But for me, the actual scheme as reported doesn't pass Occam's razor. They put a lot of effort in to develop a really, really tiny implant that you can detect by just looking at it, right? And this is a country where they have all the manufacturing capability in the world. They can do anything, right? And so if I were to actually, probably what my guess is what happened is that something did happen, but the details were changed for operational reasons to not leak the actual thing that's happening. But if I had those kinds of resources, I would develop sort of a set of through silicon via WLCSP implants that I can go ahead and put between chips. They're essentially indetectable. And I have multiple options for putting them into the supply chain. If I have to be on one side of the ocean, I can go ahead and put them all the way from the IC test and packaging to the box build site. And then if I need to have a very targeted operations in the target country, a mobile rework station costs not a lot of money. The actual tools you need to remove a chip and put them on cost about a couple $100 on the market. And within 5 minutes to an hour, depending on the complexity of the box and the amount of sort of other things they use, like glue to hold on the chip and whatnot, you can typically pull off the chip and replace it within about an hour. And so there's multiple opportunities from the courier to customs to distributor to returns and exchanges to go ahead and put a very directed implant towards particular customers. So the key takeaways from this talk, that if I were to try to put them out there, supply chains are hard even when security is not a concern, right? I have to deal with all kinds of shenanigans, fakes, and people trying to sell me stuff that isn't real, even when it's not a security issue. And in this case, the red team isn't caring about my secrets. They just want to make some money, right? So, and the interesting thing is that this ecosystem essentially has developed a large amount of commodity technology that can be readily adapted to the manufacturer of sort of implants at the end of the day. So now you can do a wire bond implant for low tens of thousands of dollars. And if you want to do this wafer level chip scale implant, it's probably a few $100,000. And also, it's got a very large attack surface. So you have everything from workers and couriers. It's a very porous transient community with not a lot of loyalty to their employers. You have distributors and factories who have misaligned interests to yours. These distributors and factories, they have a profit motive. They're not necessarily caring about your security. And then finally, the build-to-order practices that we all sort of love and take advantage of these days really extends that attack surface with great specificity over borders and across multiple companies. And so that's it.